Can we start? Yeah. Okay, thank you very much for inviting me. It's a great pleasure to be here. I'm really honored to see all these people. It's a very crowded class. And actually, I'm going to give 7 hours. So, and I'm confident that at the end of the lectures, someone is still in the room. Also, I will make my best to make everybody disappear. Okay, this set of lectures is about regularity theory. And regularity theory is something which is very classical and can be formulated in very classical things. So, for instance, very, very classical statements in regularity are that a certain function which minimizes a variational integral or solves an elliptic equation, then this belongs to C0 alpha. This means that it's locally continuous, or it belongs to C1 alpha. And so the statement, what I like in regularity is that the statements are very, very simple. And by a duality principle that many mathematicians start knowing better and better over their career, if the statements are very, very neat and simple, then the proofs can be very mean and long. I mean, it's very often the case that proofs of complicated statements are very simple, and proofs of very simple statements can be extremely long, technical, and difficult. An instance is, of course, provided by the proof of the Fermat's last theorem. We are definitely not at that stage, but you see there is a simple statement, and then the proof is extremely mean. Okay, there are several. Okay, what I'm planning to do is the following fact. Regularity theory is a very large and huge subject, so it is not the case to give an historical, and large, introduction to it. So there are large parts that are not to be covered. So I will essentially deal with regularity problems for solutions to so-called quasi-linear equations. And as, for instance, a typical example of quasi-linear equation is the Euler-Lagrange equation of a variational integral, then these are also deal with minimizers of integrals of the calculus of variations. So essentially, let me start from the calculus of variations. This is linked to the well-known Hilbert's 19th problem formulated. It's one of the famous problems by Hilbert formulated at the beginning of the last century. Essentially, you want to consider functionals defined in suitable function spaces, and then we see where we start with where I start taking competitors from. And these are functions, and in the most general case, these are functionals of this type, where f is where omega is n, and I will generally consider the case n larger or equal than 2, with n equals to 2 being actually a rather simple case, and this is defined in omega times r capital N times capital N times n. So capital N equal to 1 is called the scalar case, where every competitor, and therefore the minimizer is a scalar valued function. That's the scalar case. While capital N larger than n is called the vectorial case. So Hilbert's original problem, well, essentially, let me give you the most classical and historically established example of this. You want to minimize this integral, which is very classical, and actually this is a classical subject, and in fact the development of calculus of variations and of regularity theory goes hand in hand to the development of functional analysis. Essentially, why about the development of functional analysis? Because here the whole matter, also historically speaking, is to determine the right function space where you want to find a solution. Okay, essentially, the problem, if you look at this problem, now we know that this admits a solution, and that's the usual, the usual minimization problem of a functional. This we can call W omega. And nowadays we know that we can find a solution that solutions to this problem are smooth, provided they start from a good class. Good class means that actually these are almost always smooth, but for essentially for general integrals you have to start with suitable, in a suitable class. And there are centuries of developments, decades, but nowadays we know that the right space you want to ambient the minimization of this functional and of functionals of the following type, where f of u can be controlled by u square in terms of growth. It's a Sobolev space W12. That's a Sobolev space W12, and this is essentially, very roughly speaking, the space of L2 functions such that also the distribution of derivative is an L2 function. Now, the main problem of the calculus of variation is that you want to prove, you come up, when you minimize such an integral, then you want to know under which conditions. And actually, this is the main point where so-called direct methods of the calculus of variations come into the play. And direct methods of the calculus of variations is nothing but the classical Weierstrass theorem that you want to extend to infinitely to function spaces, essentially. So you take a function f, which is supposed to be convex, and actually this is a necessary and sufficient condition to get some of these results, at least in the scalar case. Then in the vectorial case we go to a more generally and difficult concept that's called quasi-convexity, but I'm not going to talk about quasi-convexity. So let's start with f to be convex, only depending on the gradient variable, and coercive. So this means that if this is the gradient variable, this is something like this for sure, and therefore you can prove that this is lower semi-continuous with respect to the weak convergence of W12. So this means that if un is a function which is weakly converging in W12, this means that it's the usual notion of weak convergence. Then you can prove that the limit of these kinds of functionals is larger or equal than this. This together with coercivity by so-called direct methods, that's nothing but the usual Weierstrass theorem in infinitely dimensional function spaces, then provides the existence of a minimizer. Essentially the proof is line by line the usual proof. Right? You take a bounded sequence, a minimizing sequence, then by compactness you can always extract a weakly convergent subsequence in W12. Why? Because this is bounded, because essentially it's a minimizing sequence and this is coercive. Then after this you can pass to the limit and you see that the minimizing sequence is converging to something that minimizes your function. So you come up with a minimizer which is now in W12. And now the idea, and that's this was essentially the arrival point of several decades of investigation, and one of the main points of this investigation is that you want to determine the right space you want to work with. And in fact, there has been nowadays Sobolev spaces are something that you learn from the very beginning, but they have been developed through decades of efforts by several people like Sobolev, Mori, Beppo Levi, and several other people. Essentially, Beppo Levi did a lot for these spaces. Also people like Stampacchia, but this belongs to the past. Now let me go on. Now we have a minimizer that belongs to W12. Okay? Now you want to know if, just by the fact that this is minimizing something, you can bootstrap this to something that I told you before. This is alpha, y alpha, and smoother. And smoother as long as the regularity properties of the function allow. So essentially, this is the core of Hilbert's 19th problem, and this problem was formulated by Hilbert at the beginning of the last century, and there were incredible efforts by several people, and essentially the idea, the problem is formulated in these terms. Assume that f, right, is as smooth as you like. For instance, it's analytic. Okay, so there is no obstruction for regularity or minimizers coming from the integral. Can we say that U is more regular than W12? And in particular, it's analytic itself. Essentially, this is not the real formulation of Hilbert's problem, because at that time, solid spaces didn't exist yet. So the original formulation was, if f is analytic, can you find a minimizer in a certain sense which is analytic? And nowadays, if you start from the direct methods of the calculus operations, if you start from a W12 minimizer, can you say it's even smoother and eventually as smooth as the regularity of the integrand allows? And so many people have been working on this, and starting from Bernstein, Cacciopoli, Petrovsky. I like in particular to mention Regato Cacciopoli, who is a mathematician who worked in Napoli, and he's actually my grand-grandfather in academic terms. And essentially, the point was that if a solution was known to be, in the 50s, if a solution was known to be C1 alpha, and actually of class C1, then it was known to be more regular, analytic, if F was provided. On the other hand, so this was the starting point. So if you know how to do this, then you know that it's smoother. On the other hand, you start from a W12, and essentially this is the point where Ennio De Giorgi comes into the play, because independently, and a bit later independently, Giorgi-Nash also, because they were able to fill this gap by a very subtle theory that was very much different from what was known at that time. So this was around 56. This was probably 57, something later. That's a famous story. That's the famous story between De Giorgi and Nash, because De Giorgi published this in an obscure Italian journal at the time. So the news that he had solved the problem came only later, meanwhile Giorgi-Nash was still heavily working on the problem. And it was, if I remember correctly, it was Nuremberg that was visiting Europe, and he spoke to Stampacchia, and Stampacchia reported that Ennio De Giorgi had solved this problem. The story is particularly simple, because it's particularly interesting, because Giorgi-Nash was given the problem actually by the same Nuremberg, and he worked on the problem for more than 1 year, doing heavy attempts, as reported by certain folks by Hormander. And while Ennio De Giorgi learned the problem during a walk on the mountain with Stampacchia, it was in June, and after less than 2 months he had solved the problem in a very straightforward way that I'm going to talk about in a few minutes. Giorgi-Nash came later, and he could not believe that Ennio De Giorgi had solved this problem in such a direct and simple way. In fact, at that time, Ennio De Giorgi did not even know the definition of Sobolev space. He came from the scratch. He reconstructed all the things from Sobolev space theory that he needed, and then he went to the solution. In fact, he never uses, essentially, the properties of Sobolev spaces other than those that he reconstructs in the paper. Essentially, for instance, he doesn't use what is so-called Sobolev embedding. He uses something called the isoperimetric inequality, which is known to be equivalent to Sobolev embedding theorem via integration of levels. These are, famous facts. And what is more important is the breakthrough that this theory gives, because essentially it was clear at that time that the whole problem could be reduced to the following one. Okay, you take a linear elliptic equation, which is the following one. So you take a solution to this. This is a matrix. So this is in the weak formulation. This is like this. In the distribution of form. So this is for every phi that belongs to C infinity. Okay? And with measurable coefficients. That's the point. These coefficients are measurable. This is bounded. So A of x belongs to L infinity. So it's bounded. It's elliptic. In the sense that if you do this, this is for every vector in Rn. Because let me tell you that this is the scalar case. This only holds for scalar equations, but nothing more than this. In particular, no continuity is assumed. You see, these are bounded and elliptic. So no continuity is assumed. Bounded means that you can bound from above this by a big constant. So what De Giorgi was able to prove is that if you start from an energy solution, and this is a crucial point, you have to start from something with finite energy, that is, if you start from a solution, which is in W12, and let me observe that to give meaning to this object, you don't need that the gradient is in L2, but just that the gradient is in L1, because then, you see, d phi is infinity, and therefore to make this integrable, you just need L1. So you might like to start with a so-called very weak solution, that is, U is in W11, but to hold these results definitely need that you start from a W12 solution. Okay, and then there exists alpha between 0 and 1, depending on what? Depending in a critical way by the gradient and the ratio between the highest and the lowest eigenvalue, that is the upper and lower controls, such that U belongs to C0 alpha locally, That's the result. So this is a result that breaks the scale, and it's totally new to that time, because essentially this result opened the way to the modern nonlinear theory, and essentially all the scalar results you might like to have on so-called quasi-linear equations of this type, of the type of the Euler-Lagrange equation of these functionals, that is of, for instance, of equations of this type, as you will see, plus lower order terms, then they rely on the techniques of these results. So you might like to do whatever you like, but everything relies on the techniques introduced by De Giorgi in this setting. Of course, several other things can be done also by Nash methods. In fact, De Giorgi's proof was such a novelty that people try to find also other proofs, and then 2 or 3 years later, or 5 years later, Giorgi-Moser came out with a new proof, including the validity of Arnold's inequality for this function. Arnold's inequality tells you that if you have a non-negative solution, then you can bound the sup over a domain of U by a constant times the inf of U over the same domain, and the constant only depends once again on these parameters. In particular, this is stronger than Hilbert continuity. It can be easily shown that this implies the Hilbert continuity of a solution. Nowadays, this is called the classical De Giorgi-Nash-Moser theory. Later on, this has been extremely developed, and as I told you, it's not only important the result, but also the innovative techniques, as was eventually noticed by several contributors, amongst which I would like to Lagichenskaya and Rujaltseva. If you take the classical books of Lagichenskaya and Rujaltseva, they extend to, in a very strong way, the ideas of De Giorgi to several kinds of elliptic and especially parabolic problems. In fact, this was one of the main motivations of Lagichenskaya and Rujaltseva, because there's one classical book by Lagichenskaya and Rujaltseva, and another classical books by Lagichenskaya, Solonnikov, and Rujaltseva. And one of their motivations is to go beyond Nash ideas that they judge to be a bit opaque, and using the Giorgi's method, applying them to the parabolic setting. And in particular, Lagrange and Realford have made important observation that although the original result of the Giorgi was assumed to hold for linear elliptic equations, then it actually, the proof is intrinsically nonlinear. It doesn't use linearity. It uses something that we shall see in a few moments, which is called Cachapa inequality. And essentially, using this inequality, you can do everything, and you don't use the fact that you have a solution of an equation anymore. Another person who deeply understood and developed these methods is Luis Caffarelli. And it's due to Caffarelli okay, many things, of course, but the fact that he exploited very much that the Giorgi's ideas are formulated via density conditions. And in fact, there are a lot of density conditions of the Giorgi type in the papers by Caffarelli, where he applies these to free boundary problems. While another person I'd like to, it's Emanuele Di Benedetto. Emanuele Di Benedetto applied the Giorgi's ideas and extended to certain type of equations of parabolic Laplacian type. I'm going to talk about this later. And this is also another very important development because he introduced something like intrinsic geometry for parabolic equations, and he proved, and he also, exactly as Caffarelli, strengthens on the fact that you have density conditions in the Giorgi's idea. Okay, so once you gather these methods, you eventually abandon the fact that you have a linear equation, and you go to nonlinear methods. That's the point. Okay, so let me give a look and explain why this at that time was a completed break of the scale. And let me also tell you why this was the missing point in the solution of the 19th Hilbert. So, what are the classical methods? And let me go back to the history of elliptic equations. And what is the most, important and classical elliptic equation, the perfect equation? It's of course the Laplace equation, or the Poisson equation if you allow a right-hand side. So, this is the following one. And you can solve it in all the ways you like. You can start it. Solutions are called harmonic functions. They verify a lot of properties. For instance, as a consequence of mean values formula, you know that they verify mean value properties. And mean value properties are things like this. They easily imply that, for instance, if you take a ball, and you take half of the ball, and you take the sup of the modulus, then this can be bounded by the integral. But as you know, every derivative of a harmonic function is still a harmonic function, so this actually holds for every derivative. Where this is let's say, multi-index of the meaning of order k. And there will be a constant here. Actually, there's no constant. This is called L1 L infinity. L1 L infinity inequality. That's very classical. And that's a basic property of harmonic functions. So harmonic functions are such that things that hold in average are by regularity commuted in things that hold uniformly. You see? You are controlling the L infinity norm that controls uniform properties by an L1 norm that controls properties in average. This is a quantitative formulation by several known facts of harmonic functions, and the easiest fact is that an harmonic function that converges pointwise then converges uniformly together with all the derivatives. That's another way to commute things that are holding pointwise or in a weak sense, in things that are commuting in L infinity sense, so uniformly. So this is a quantitative fact. So at that time, this was known, and for instance, how to deal, which was the only way to deal with solutions of this type, of this equation. Well, you know that what is the Laplace equation? Well, this is the diagonal matrix. So if this is the diagonal matrix with constant coefficients, 1, 1, 0, 0, this is this one. So you know everything when this is the diagonal matrix. But on the other hand, by ellipticity, if you assume that this is elliptic, you know that when this is a constant, so it's just a constant matrix, then you can make, and in particular, for instance, it's symmetric, you can make a change of variable, for instance, assuming it's symmetric, you can make a change of variable, and you can frame it as a harmonic function after changing coordinates, right? So this means that you can still deal with constant coefficients. What is the next step? The next step is where A of x is continuous. Since you're looking for local properties, you might wonder, you might say that you are not interested in what happens in the whole domain, but just in very small parts of the domain. Now, in very small parts of the domain, very small balls here, the continuous function behaves like a constant. So you can do something which is called constrict. And this is at the base of perturbation methods. Perturbation methods are the following one. You take a small domain, right? Then you say, okay, this is continuous. So it cannot be very much different than a constant. So this, and then I consider this equation where this is, for instance, the function evaluated at 1 point, or just the average, take 1 point. And you take this solution. Now this solution is a solution to an equation which has constant coefficients, so it's harmonic in a sense. So now this is regular. Now the basic property of ellipticity that you can easily frame using Fourier transform, but using also monotonicity, is stability. Stability means that if you make a small perturbation in the data, so there will be a small perturbation in the solution. That's the basic property of ellipticity. Whatever you're doing, you're using this fact in very many situations. So this means that if this is good, since W is close to U, then also U must be good. And this is a standard perturbation method that eventually led to so-called Schauder's estimates. Schauder estimates that should also be called Schauder-Cacciopoli estimates, because it is less known that Cacciopoli developed this independently. So now you understand what is the break of the scale. You can treat constant coefficients by changing variables, by using fundamental solutions the way you like. You can still continuous coefficients using perturbation, because something which is continuous is locally constant, and therefore ellipticity provides you closeness of solutions if operators are close. But then you cannot go beyond. You cannot get further, you cannot get better than this. In particular, if you have measurable coefficients, then these are very rough coefficients. And this was totally unknown. And then the Giorgi's theory uses this. Okay, now let me tell you why it was important to understand that the solution had continuous derivatives. And the Giorgi proved directly that they are Hilbert continuous with a potentially very small alpha, but positive alpha. Okay, so let me go back to the variational integral, which is the following one. In order to be well posed, and in order to have some minimal regularity, and also in order to get existence of solutions, you want that this is convex. Okay, convexity of this guy means that the second derivative gives a positive defined matrix. So it's larger than 0. You have to reinforce this if you want regularity, otherwise it's very simple to provide examples of minimizers which are totally irregular. For instance, if the second derivative is 0, that is f is flat, then you can get arbitrarily that function that minimizes this integral, because the gradients are given, are attained in the flatness zone, and they can do whatever they like, and the function can be zero. So you reinforce it with a suitable solution of ellipticity. Let's say it's larger than the eigenvalue. So that's the ellipticity. This is a way to write this one. Okay, this is a way to write this one, and of course, this is a matrix. Okay, now, what was known was the following one. At this stage, you can introduce the so-called Euler-Lagrange equation. The Euler-Lagrange equation is very simple. You perfectly know that when you minimize one function's variables, then in order to get minimizes, you look, for instance, at critical points. Critical points means that you want to say that if you have a one function variable g, you want to study the points where this is 0. And you know that if g is, for instance, strictly convex, these are the same things as being minimized. Then you do the same thing using, for instance, so-called variation. You take phi, which is C infinity here. You consider the following function, p, which is given by f d plus d phi. That's a variation. As you see, if u is a minimizer, then this is a one function variable that attains its minimum at 0. So you want to study this. And this is the same, developing under the sign of integral, that doing this. So that's the gradient of f du. So this is a nonlinear equation. So it's a nonlinear equation that in distributional form looks like the following. Divergence of f of du equal to 0. And in fact, we will then eventually see several equations of this type. Okay, now you want to go on further. You want to go on further, and you further differentiate this equation. This was known by so-called difference quotient methods. For instance, it's well known, the famous Nirenberg's difference quotient methods. Essentially, what you're doing, you substitute this with a derivative. You plug in this. You integrate by parts. And you get this. And now if you call W ds, then you get a linear elliptic equation, formally, a linear elliptic equation. This can be written as a of x dw d phi equal to 0. So this is an equation exactly of this type. And now a point. What you're trying to prove is that the gradient is continuous. What are the coefficients? The coefficients incorporate the gradient. You see, gradient is here. So you can have a very smooth f, but if you don't know that du is continuous itself, you don't know that a of x is continuous. And you cannot apply the perturbation method. Now you can immediately see what is the stacking point at that time. Which was the stacking point at that time? You differentiate the function. This you can do by difference quotient. This is still interesting, but it's not as deep as that one. Then you come up to a linear elliptic equations whose measurability of coefficients is given by the fact that the coefficients are dictated by the internal dependence of the gradient, and the gradient is not known to be continuous because this is exactly what you want to prove. So there's no way then you can afford this problem with the perturbation methods, because perturbation methods would mean that this object is continuous, but this is continuous if and only if in general du is continuous, but this is what you want to prove. And so at this stage, the Giorgi comes up with this problem, and therefore the final missing gap in the theory is proved, and once you know that the gradient is continuous, then you can use the other methods to prove that it's is as smooth as the regularity of the integral f allows. So this is the story. Okay, as I told you, it became obviously clear that the methods of the Giorgi are nonlinear in nature, and in fact, they apply to general equations, which are assumed to be nonlinear. And now the point is that if you look at the Giorgi's theory, it has completely different methods than the standard theories that have been developed since then, at that time, but they come up with the same a priori type estimates. In particular, we will see that the L1 and L infinity estimate holds for the solution. Okay, what I'd like to tell you is that it was noticed almost immediately that the same proof, and this is actually the approach of the Ladichensky and Ryaltsev, holds for general nonlinear equations of this type, provided some generalized conditions of ellipticity hold. And in particular, this has to be bounded, LZ, plus you can allow lower order terms. But I'm not discussing the occurrence of lower order terms because this is mostly on the technical side. It can be quite mean. If you want to do sharp things, it can be quite delicate. But as a first strike, I'm not going to discuss the occurrence of lower order terms. So this is the average. This is of course a vector field times Rn times R times Rn and goes to Rn. And of course the weak formulation of this equation is the following one: x u vi 0. I'm using Einstein's convention of the double summation when double indices occur, and this for every phi infinity. And of course the monotonicity, that is the ellipticity, is prescribed by doing the following fact: when you take this guy controls this point. That's the thing. That's the story. Of course, in the linear case, you're taking a of I of x like a j x vj, where this is the gradient variable. That's a particular case. So the theory still holds, and the proofs are verbatim the same. So the proof of the Giorgi is non-linear in nature because he never uses linearity, and it actually goes even further, because as noticed, and this is a very useful observation by Ladichensky and Ryaltsev, it works for functions that belongs to so-called the Giorgi's classes. These were introduced by Ladichensky and Ryaltsev. Okay, what are the Giorgi's classes? The Giorgi's classes are functions satisfying the following thing. So U has to belong to W12, and this is the very minimal condition that we're requiring. So these are so-called energy solutions, because their energy, that is the L2 norm of the gradient, must be finite. Well, then they have to satisfy the following condition. We say that U belongs to, okay, this is a simplified version of the Giorgi's class, simplified in a sense that these are the Giorgi classes cooked up for the case where you have no lower order terms, as in this case. You have simpler lower conditions, because if you have lower order terms, then there will be correspondingly lower order terms in the inequalities I'm going to state, but we don't mind these lower order terms. Okay, so the Giorgi class is actually GB plus and a constant C, where C is a parameter. if and only if you take du square over the level set AK rho. Let me tell you what is this guy. And this is less than or equal than the same constant, r minus rho. Oh, sorry, this is actually very, very small. So let me rewrite down. If you have the following thing, you can bound on this set less than or equal than a constant r minus rho squared u minus k plus squared. What is k plus? And this is on the same set r. What is u minus k plus? U minus k plus, it's the maximum, u minus k and 0. So in a certain sense, they tell you that on each and this is the set where this is. So this means that you belong to the Giorgi's classes. So the Giorgi's classes yields surprisingly all the regularization features eventually leading to C0R. This is DG plus. DG minus is the following one. Actually, one introduces DG plus and DG minus because they, in a certain sense, correspond to super solutions and to sub-solutions, and I'm not going to deal about this. If and only if du square dk, and k, of course, is a positive object. Dk rho is less than or equal than c r minus rho square u minus k minus squared a k rho, and the u minus k minus is defined as the maximum between k minus u and 0. So this tells you, well, they are what they are. Okay, they eventually are a truncation version of the classical Cachapa inequality. The classical Cachapa inequality is the following one. You take d over r over 2, u squared, and then you can prove this. This is Cachapa inequality. Also called reverse Poincare inequality. Why it's so called reverse Poincare inequality? Because Poincare's inequality allows you to control u by the gradient. Here you are doing the opposite. So the minimality of the function, if you look at this, it's seen by the fact that if you want to estimate the energy, well, if this is the height you're starting, the energy is in some sense minimal because it's 1 over r. So this encodes a lot of properties. So the Giorgi's beautiful idea was to translate these also after looking at some papers by a Russian mathematician called Sigalov. Then he introduces these classes. The Giorgi's introduces this property, and then everything comes from this property. In particular, if u belongs to dg plus intersected dg minus, which is called the full de Giorgi's classes, then this implies that this is C0 alpha for alpha depending on what? On the dimension L, of course, and on the constant C, that is the data. Constant C is the one occurring here. So this is the truncated version of the classical Cachapa type inequality. So we will go on in exploiting a bit only a part of the Giorgi's proof, because it's very interesting, because it's the real novelty at that time, and the breaking of the scale was given by the fact that there is no perturbation, nothing whatsoever, but there's a nonlinear iteration that the Giorgi invents, and that eventually leads first to establish that U is locally bounded, then eventually that U is locally Hilbert continuous. Philosophically speaking, you know that a way to prove that solutions of elliptic equations are bounded when you have a certain bounded boundary datum, it's the maximum principle. So an harmonic function attains its maximum and its minimum on the boundary. How do you prove a maximum principle when you have monotone operators? Making truncation. So these are, let's say, local formulations of a maximum principle and the idea, the deep idea of the George is that you can start an iteration of this some kind of maximum principles using the isoperimetric inequality, that's Sobolev and Daejeon theorem, and then this gives a self-improving property that at the end leads to first establish that U is bounded and then it's locally Elder continuous. Okay, and this is really at the core of the analysis of the regularity theory of this theory. Because why? Because then of course you can extend now. You have more delicate equations. For instance, you might allow lower the terms, having a right hand side equal to something, and then in the definition there will be lower the terms here. But then the things work as long as the sharp theorems are needed. Of course, you can have degenerate equations. You might replace these by t minus 1 and t. And in this case, you are considering the variational integral u to the p, whose Euler-Lagrange equation gives the p Laplacian operator. And you can extend formulating the De Giorgi's classes at level p. So you want to put p here, and p here, and they still work. So there's no difference whatsoever in the proofs. You can go very further. And even if you want to prove that solutions to, for instance, the Euler-Lagrange equations of this function are C1 alpha, as we shall see later, then you can cook up a suitable version of the Giorgi's iteration method that allows you to get this result. So the method is very general and leads to a lot of interesting consequences. And let me go a bit into this method. So we perfectly see what is the definition of the Giorgi's class. It's this kind of truncated Cachapa typing equality. So you remember always that you are doing something which is the opposite of what it happens. With Poincaré, you control a lower order term with a higher order term, as it is natural to do. Here you are controlling a higher order term with a lower order term. But if you think better, this is the first sign that solutions of these equations, they share a lot of properties with harmonic functions, like for instance the L1 L infinity estimate. What is the basic property of harmonic functions? You have pointwise convergence, and then this convergence suddenly becomes uniform, and also the gradient becomes uniform. And then, what is the classical property of harmonic functions? You can bound the gradient with the first derivatives, right? And so that's the same. Something which occurs for u suddenly occurs for higher order derivatives, for the derivatives. So that's a first sign that so you're going towards emulating the properties of harmonic functions for solutions to a nonlinear equation. Okay, now let me see what are the main steps of the Giorgi's proof, because these main steps are very, very interesting, in my opinion, but not only. So the first thing that the Giorgi proves is that if u belongs to dg, then u is locally bounded, and the following inequality holds. Look. So you see, everything is local here. All the estimates are local in nature, and no appeal to boundary regularity whatsoever is going to be made here. Everything is purely local. So things that can be, of course, extended up to the boundary, provided the boundary is regular enough, but then this is a consequence of the main local fact. What is and then when you know that u is bounded, then you prove that u is in L infinity implies u is C0 alpha. U is C0 alpha for some alpha, depending on n and on c, as we said. Look. And this is the crucial point where density considerations have to be used. Density property. It is interesting to see that at that time when the Giorgi cooked up the proof was working for these function classes. Then using the equation, Moser proved the validity of Arnold's inequality, many years later, in '83, if I remember correctly, Di Benedetto and Trudinger proved that a function that belongs to a non-negative function that belongs to the Giorgi's classes satisfies Harnack's inequality too. So there's no point in particular to appeal to the delicate BMO properties of used by Giorgi-Nash-Moser in his proof of Harnack's inequality and on the so-called breach lemma. Let me just recall you that according to a principle of conservation of difficulty in mathematics, if you look at the proof of Giorgi-Nash-Moser of Harnack's inequality, then you will see that at a certain stage he uses the John Nirenberg's BMO argument. Because he proves that certain functions are BMO and then they satisfy other properties, and then he concludes with the Harnack's inequality. This is not, and you know that this John Nirenberg's inequality for BMO function is not an easy fact. It's made on an iteration or an application of iterated versions of Calderon-Zygmunt covering arguments. So in a certain sense, they have to cover the level sets of a certain function. They have to cover the level sets of a certain function. This is not needed in this approach, which is certainly relying on the Giorgi's ideas. Why? Because the idea of the Giorgi's classes incorporates automatically the information about level sets. When you start from a De Giorgi class, this is B. Here B is it's U less than K. When you start from a De Giorgi classes, you get immediately an information on level sets of the function. And therefore, you can have so-called expansions of positivity and conclude, as Di Benedetto and Trudinger did, using a different version, a density version of Calderon-Zygmunt covering lemma, which is called Krylov and Safonov's lemma, that in fact incorporates the ingredient inside the BMO proof of John and Nirenberg. So this is a much more straightforward way to get Harnack's inequality due to so-called expansions of positivity. Expansion of positivity and the Krylov and Safonov covering argument. Actually, Krylov and Safonov it's not really a covering argument. It's a decay. It's a density argument. It's actually a paper that I strongly recommend to look at. It's Di Benedetto's studio, 83 or 84. It's on Analyse non linéaire. Okay, but now let me go, and now let me briefly go to this fact. So because I'd like to give a hint of the proof, because these iteration mechanisms and these density lemmas are very, very delicate and basic. So they really need to be seen at least once in a lifetime, also for those who are not bound to study elliptic 2D regularity. Yes? Okay. Okay, let me show you a simple proof of Cachapa inequality when no level sets are considered then whatsoever. So how can you prove Cachapa type inequality? Then you have this function, a of h du, d phi, which is the weak formulation, the distributional formulation of your inequality, right? And so this holds for every phi, which is C infinity, omega. But of course, since you're dealing with an energy solution, so U belongs to W12, then by a trivial density argument, this goes on holding for W120. So in particular, you can take a ball, B, dr. You take a cutoff function that lives here. So it's theta equals to 1 on B, R over 2. Eta is smooth and doesn't live outside the ball. And of course, the gradient, you are not stupid to take a very large gradient, right? Now, the best you can do is that the gradient can be, let's say, bounded by 4 over r. I guess if I'm not, I mean, a constant over r. Yeah, you want to pass from 1 to 0 in a r over 2 time. It's not very difficult. So, as a test function phi, we take u times u, and then of course the gradient of phi is equal to eta squared. It's eta squared u plus 2 eta d eta and so forth u. Okay. That's it. Right. Okay, if you plug this inside, then you get that a of x of u du theta squared is equal to minus a of x a of x du u du theta. So, okay, this is the first term, I1, this is the second term, I2. Okay, as usual, I1 can be estimated from below using ellipticity. And if you use ellipticity to bound it properly, then you get that I1 is I1 is larger than u squared theta squared. That's ellipticity. That's nothing but the ellipticity properties of a of x. Because you see here, you see a of x du is bound to u squared times u, and then you have theta squared. Well, I2, its absolute value can be estimated by C, the absolute value, the maximum of this guy, by eta du. So by Young's inequality, this can be estimated by mu squared, exactly the term you have on the left, plus constant d eta squared, u squared, omega. Now, this can be reabsorbed into the left-hand side, and what you come up with is u eta squared less than or equal d eta squared u squared, which is the classical formulation of Cachapa type inequality. Look here, you switch the gradient to the solution on the test function. It's a sort of duality inequality. If you recall that eta is equal to 1 on dr half, and the gradient of eta can be bounded by c over r, then you exactly conclude with the Cachapa inequality you are willing to prove, that is, the one I wrote before on the blackboard, is du c over r2 u squared. At this stage, it is very simple to understand how is the proof of this guy, of this inequality, and of this inequality. You don't have to do anything different but choosing as a test function u minus k plus minus theta squared. And you do the same. So that's a very basic factor, and that gives you the first ingredient. That's the Cachapa type inequality, also called the energy inequality, because that's the basic tool you like to use here. Okay, it's nothing very difficult, but I mean, you see the conceptual jump to understand it from this inequality, and from this inequality, that this inequality leads to Hilbert continuity is not very clear. I won't tell you whom, but let's say a leading mathematician who spoke to the Giorgi many years ago told me that he asked the Giorgi how he came to the idea that the Cachapa inequality on level sets implied the Elder continuity. He just replied in the usual way he was used to reply, that is, it is obvious. A variant of his reply, one of the variants of his reply is that, oh, Professor De Giorgi, how come that this function behaves in this way in your proof and blah blah. And then how come that this axis, once the axis is small, then it starts being smaller and smaller, and this was the epsilon regularity theory and blah blah. And then another way he was used to reply was, what else would he like him to do? I mean, what else he can do? I mean, you see, that's a very interesting thing, right? Okay, so let's see how you get L infinity, because now we are really at the core of the Giorgi's ideas. Because actually, really, you see the De Giorgi's ideas in actions when you prove the L infinity and the local estimate. So what we want to prove is the following fact. Is the fact that you get an L1 L infinity estimate exactly as for harmonic functions. Well, I know that that the title of this course is Recent Progress in Regularity. Well, if you adapt recent to the 50s, this is very recent. But I promise that the things will get more modern along the way. Also, I don't promise that they will be deeper than this. Okay, so the first thing we want to do is now to prove that U satisfies an L2 L infinity inequality. So if you get U that solves the previous equation, and once again U that starts being a W12 solution, it is really essential, as I'll briefly mention later, then you get the following inequality, which is true. The sup over BR over 2 of U is less than or equal than the sup of U squared BR. Once you know this, then the L1 L infinity follows by a simple iteration length. So this implies, in particular, the L1 L infinity by a simple iteration. So it's not very difficult. You interpolate L2 between L1 and L infinity, and then you reabsorb L infinity, and then you get L1 on the right side. So this is just interpolation. So once you get an improvement, you get all possible improvements. That's the point. Okay. In particular, let me prove that that if U belongs to DG plus, then this extends to the sup of BR over 2 plus BR over 2. So this is a version that is cooked up for DG plus. The same thing holds for DG minus, DG plus DG minus, then bounds what you get. So this is the positive part of U. Oh, let me just denote it by this. Sorry, this is bad notation. So this is the positive part. If you replace DG plus by DG minus, then you get minus U. So if you are in DG, then you can bound the sup and the inf, and then you can bound the absolute value. Right, same form. So I'll give the proof for DG plus. Okay. First of all, now I need, let's hope not to make too many mistakes. Susie, you tell me when I should stop, right? When should I stop? 3 o'clock. So I should stop it now. So actually I knew when I had to stop. So I was asking you to, in order to get a kind reply of the type, you can stop when you like, but you are very strict 3:30. Yeah, because there was a question and answer room here, but okay. Something disappeared from this timetable. Are you sure it's 3 o'clock? No, it was supposed to be 1 hour and a half today. Question and answers, or let's say that, yeah, there is 30 minutes, but do we want to have these 30 minutes really for question and answers, or do we want to have... Yeah, let's go on with this proof, and then I would say that in 15 minutes I hope it's going to be worked out. Well, because you see, I would imagine 30 minutes of question and answers after several lectures, but not after 1 hour. You see, having 30 minutes of question and answers after 1 hour either means that you solved the Riemann hypothesis, or that your lecture was very, very, very bad, because half of the time goes in questions to clarify obscure points. So it's the case that it goes on. Okay. Okay. Let me go to proof. Okay. First, let me first consider the point that you can assume that BR is centered at 0 and has radius R1. Otherwise, if the BR you're considering is like BR at 0, then you switch to the new function Rx over R, and this also similar equation. But you know, this is x in B01, this is u tilde of x, and the gradient is exactly as the gradient as in the other one. This is called the blow-up of the function. This solves a similar equation with coefficients given by a of x 0 plus r of x. Okay. But since you're dealing with measurable coefficients, if you blow up measurable coefficients, you don't lose anything. You are already at the worst possible thing, you can only gain. So we can consider r equal to 1, and that's the point. So we want to do 1/2 times b1. So we immediately do a scaling argument, and we reduce to b1. So this can disappear, and that's the first thing. So let me take 1/2 less than sigma less than tau less than 1. Let me consider a usual cutoff function that belongs to C, b sigma plus tau over 2, such that on b1, on b sigma, and all this balls are centered at 0. So we are considering balls that are centered. I mean, this is b tau, and this is b rho, b sigma. Okay, and this is b1/2. So it's 1 sigma tau 1. So d eta, it's of course the least time you need to pass from 1 to 0 in tau minus sigma. So it's bound by a universal constant over tau minus sigma. You can take it 4, and we take psi. It's called eta u minus k plus, and k is larger than 0. So we take this truncation, and we apply, and we use the fact that u satisfies with the Giorgi's plot. But before doing this, let me do the following trivial facts. I do consider a k sigma u minus k plus squared, and what do I do? This is less than or equal than psi squared dx of the full ball, because you see psi eta is equal to 1 on this larger ball. This is larger ball, one which is in the intermediate ball, and this is a Sobolev function. Therefore, a Sobolev embedding theorem, you know that W12 embeds into L2 star, which is n to n minus 2 when n is larger than 2. Otherwise, it's any number when n is equal to 2. Let me give the proof for simplicity when n is equal to n is larger than 2. Then otherwise it's even easier. Okay, then I can gain measure from here. I can gain measure doing up to 2 star. 1 over 2 star, and this is a k tau 1 minus 1 2 star. Why? Because here I'm on k sigma. Tau is larger, so I'm just enlarging the okay, what is the gradient of psi? The gradient of psi is, what is psi? It's the eta, and therefore this is less than or equal than du squared k tau sigma plus tau 2, because it just leaves, eta just leaves on these balls, 0 outside this ball, plus 1 tau minus sigma u minus k plus squared. And here I'm estimating essentially, because the gradient, what is the gradient of u? Is the gradient of this guy, which is the gradient of u, of course, of the level set, because it's k times eta, and eta is less than or equal than 1, so I estimated this by 1, plus u minus k plus times the derivative of eta. If I recall this estimate, then this is what I come up with. And this is a k tau over 2 over n, because 1 minus 1 over 2 star is 2 over n. From now on, I will call epsilon 2 over n. Okay, now look here. And of course, this is 1 over 2 star. No, it's nothing here. Because this is 2. Yeah, that's correct. Okay, now you see that we have 2 terms, right? And now we use the Cachapa inequality. The Cachapa, what is the worst term here? The worst term is the one featuring the gradient. And now, by Cachapa inequality, this can be estimated by exactly the same thing. And therefore, this is what you get. U minus k plus squared on a k sigma dx is less than or equal than a constant c a k tau epsilon to tau minus sigma squared u minus k to ak tau. You can enlarge up to tau. Notice that you have the same thing here, You're losing a lot because you're passing from sigma to tau, but in a controlled way, while you're gaining part of the measure. So that's the basic, now that's the basic inequality. See, you see, same terms with a controlled blow up when you switch from one ball to another, but then we have a piece getting the estimate, getting a measure of the level set. So you see, there's a competition here, because if you are imaging that u is bounded, a posteriori u must be bounded, then this is becoming smaller and smaller. And if you think that you want to apply this on a sequence of k's, on a sequence of levels, then this is accelerating the convergence when you go to the maximum. So assume that u is bounded, a posteriori must be bounded, so you believe it is bounded. So you apply this with a sequence of k's that is converging to the soup, right? So this is accelerating convergence. Of course, you have to take care that this is controlled, but this is what we are doing to do. We are going to do. Okay, now let me use Chebyshev inequality to get the following thing. How can you bound a k tau? This you can bound. This is u minus k u minus h, k minus h, if you take h less than k. You take another level, an intermediate level, you go a bit below. And plus, plus. So this can be bounded by what? This can be bounded by u minus h over this guy, h minus squared, squared. So you can, at the end, come up with the following inequality, that a k tau can be bounded by, yeah, by exactly this inequality on the smaller set a k tau, because you're enlarging. It's k minus h is smaller, and then you are just on this. So what is the effect now? The effect is that now this measure gives you a bad term, k minus h, but also a good term, this one. So let me plug in this inside here, and what you get is the following inequality, u minus k squared, a k sigma, dx less than or equal 1 over the bad object, this is k minus h, 2 epsilon, tau minus sigma, squared, and u minus h, a h tau, but to the 1 plus epsilon. Now look here, you have one object, you have something that looks very similar, but to 1 minus epsilon, 1 plus epsilon, and these are the bad objects. Right. And now you start seeing what is the nonlinear iteration. Now, observe one thing. What is the behavior of a sequence that does the following thing? Assume that the first point, the first object, the first term is smaller than 1. What is the behavior of a positive sequence doing the following? Goes to 0, right? Because you start with something that is less than 1, then the next one will be much smaller, and it goes to 0 geometrically fast, right? Now this looks a bit like this, but with bad terms. But these bad terms are probably under control if the iteration is geometric, and that's the key point. The iteration will be geometric, and now we cook up a behavior like this in order to see that for suitable choices of radii and of levels, this is converging to 0, and then you get a subbound. And that will be the end of the lecture. Okay, to do this, we do the following. We start taking d larger than 0. We start taking level sets that are approaching d, ki is 2d, 1 minus 1 to I plus 1. So when I goes to plus infinity, this goes to 2d. Then we take these sigmas, that is the radii, something which is interpolating between 1 and 1/2. You see, when I 0, this is 1. When I goes to plus infinity, this is 1/2. So what we are doing is the following thing. We are going from d1 to d1/2. So this is the place where we want to estimate the L infinity norm of u with a sequence of balls. And then we apply the previous fact with the following choice. I plus 1. Tau is of course bigger. It's larger. K is ki plus 1. H is ki. So we decrease the ball and we enlarge the level. If we do this choice, then you see this is blowing up geometrically. Tau minus sigma is blowing up as 2 to the I this is blowing up geometrically, but then you believe that the rate of this convergence is killing this and letting everything to zero. And in fact, if we let this 1 over b squared a ki sigma I u minus ki squared, then it is not difficult to see that this commutes into this. C 2 I 2 1 plus epsilon phi I 1 minus epsilon. So this is nothing but this, but with the additional presence of something which is blowing up geometrically. You see? Now the point is that in order to go to zero, you just need that the first one is less than 1. Here, in order to go to zero, this sequence must compensate the potential blow-up of this other term. And now there's a lemma that you can prove by exercise. Then if you take the first number less than or equal than c minus epsilon b minus 1 over epsilon squared, and where actually this is 2, I mean, you have a general, let's say, a general lemma. Let me point out this lemma outside because this lemma works by itself. Assume that you get a sequence. Assume that you get a sequence xi such that xi plus 1 is less than or equal than c b I xi to the 1 plus epsilon. Then, if the first term is not, and these constants are of course larger than 1, otherwise you put 1. Now, if the first term is smaller than this one, so if it's not only less than 1, but it's much more less than 1, as these terms are dictating, then this goes to 0 geometrically. And now this is exactly the case if the first term is small. If we take the first level to be 0, then the first term will be, and if we choose d equal to u plus squared over 1/2 times a suitable constant, so if this is large enough in order to make the first term that has this at the denominator less than 1, less than what is needed, then this will go to 0. And phi I goes to 0. But what does it mean that phi I goes to 0? When phi I goes to 0, the level sets are approaching d. The balls are approaching d1/2, and you'll get u less than 2d. But what is 2d? This one. This will be u plus, of course. What is this? It's exactly the L1, L2L, the L2L infinity estimate we wanted to have. So the idea of the Giorgi is actually you take a sequence of levels, a sequence of balls, you get a nonlinear iteration where you get, let's say, this infinite sequence of maximum principles. You approach something, and the fact that you're approaching something is given by the fact that you are accelerating the convergence at each stage by this 1 over 1 plus epsilon. That's it. And then, if the first term is small enough, that is this, that you make with this choice, that eventually realizes the final estimate, then you approach to 0. Last observation, it is obviously clear not only that everything is coming from Cachapa's inequality, but that in all this proof, the fact that epsilon is equal to 2 over n is completely immaterial. Any epsilon larger than 0 false, because the iteration is geometric. In particular, we shall see later on some remarks concerning a possible fractional version of the Giorgi's iteration that allows to get a singular estimate, but when you involve not a classical Cachapa type inequality, but rather a fractional Cachapa inequality. We'll see, I guess we have questions and answers now. Oh, questions, I don't know answers. It's just to normalize it. Just to normalize it. It's aesthetics. Because then you see, you'll get a constant anyway. This constant serves exactly to make sure that the first term is very, very small. Because then if the first term is small, something that you can always do, making larger the constant and eventually worsening the final estimate, then the geometric convergence lets you to 0 anyway. In the Giorgi made millions of conjectures, guy. I mean, and you are just, he was making several conjectures every day. And I can tell you, entire careers were built on those conjectures. Okay. Yeah, it's a famous conjecture saying that the same should be true. That is, U is continuous rather than Hilbert continuous. Not because you see, the coefficients are, I think, assumed to belong to an exponential space. That is, they are not. I don't remember exactly the coefficients, but essentially you are replacing a of x in L infinity by a of x in a suitable exponential space. That is, that you get x of a certain constant of u of du of a certain constant of a of x finite, which is some sort close to an infinity. And then, since you lose boundness of the coefficients, you lose the Hilbert continuity, but you still keep the continuity. This is linked to an even more precise conjecture we made on the decay of the level sets that we shall see tomorrow. I mean, you know that when you approach the maximum, in order to get a vicinity of a vicinity to the, in order to get, if I remember correctly, to get the measure of the level sets is grows polynomially, then you have to approach the maximum dyadically. And then he conjectured that this is not the case for solutions of equations, that you can approach it not only dyadically but just polynomially. But then he made the conjecture that this was not holding for general the Giorgi's classes, but rather for solutions. So he stated this for solutions. We should have asked him. Once again, many people asked him, and he replied, well, it is sufficient to do the computations. Do the computations. These computations were never made up to now. And then the gradient is bounded again by u. That's the real key point. No, eta is 0, the boundary. Eta is 0. Yeah, eta was C infinity 0 b and you apply the Sobolev inequality to this. So this is 0 bound. And in fact, this is where the additional lower order terms coming from, but this is not really important. It's the gradient that matters here. No more questions. So you see, we invested in the right way, giving more time to the proofs and less time to the questions. So this was the right investment. And we still, but not the optimal one, because we still have 4 minutes. So probably we should have started a bit later.